process variable that we are going to be looking at is flow. So how do we measure the flow of fluid through our pipeline or through a section of our pipeline? So we are going to be using the differential pressure flow meter. That's what we are going to be looking at. So what this meter does, or this system of measuring flow does, is that it creates pressure difference, okay, across a section of the flow stream. So with that pressure difference, we can determine the flow rate of the fluid through that section of our process or of our pipeline. So that is exactly what is represented here. So for us to create that pressure difference, we place a restriction on the line of flow. This is an orifice plate, a circular plate with an opening in the middle. So that plate, once it's placed on the line of flow, it momentarily stops the fluid, okay, at this particular position. That is what we are seeing here. So it momentarily stops the fluid at this restriction, at this particular position. And once that fluid is stopped, the fluid velocity will come down. And when we apply Bernoulli's principle, the pressure will do what? The pressure is expected to go up. Then, as you constrict or restrict the flow to go through the orifice, okay, constrain the flow through the orifice, what will happen is that it's like you are throttling the flow. So as you are throttling this flow, that will do what? Increase the velocity, okay, on the downstream end of this orifice plate. And once again, once we apply the Bernoulli's principle or Bernoulli's equation, you'll see that that increase in velocity will now be converted to reduction in pressure. And that is what we are seeing here. Assume this is a fluid or liquid manometer. You see that we now have higher pressure upstream the orifice plate and the lower pressure downstream the orifice plate, okay? So the point with the lowest pressure is what is called the vena contrada. So when you look at it, that means the pressure here, P1, is expected to be higher than P2. So how this works is that this differential pressure that you have created, okay, changes with change in the flow velocity or the flow rate, okay, across this section of your pipeline. So as the flow rate is increasing, that differential pressure will be increasing. As the flow rate is reducing, the differential pressure will be reducing. So your meter will be calibrated to give you flow reading, considering the pressure differences, okay, that has been created because of the restriction. That is exactly what we are seeing here now, okay. So you see, as the flow rate is increasing, what happens? You'll see that the differential pressure, okay, across the orifice plate will be increasing. So the flow rate determines the differential pressure. So that is what we are seeing here also. So you see the orifice plate. This is you see the pressure increasing because of the momentary velocity reduction. So as it is throttled through the orifice, the velocity increases, and as the velocity increases, the pressure will go down. So we see differential pressure of about 14 psi here. So like we said earlier, this differential pressure, okay, increases with increase in the flow rate and reduce with the reduction in the flow rate also. So that differential pressure could be sent to an differential, there is a DP transmitter. In the DP transmitter, you see that that differential pressure is converted to current signal, okay, amplified and then sent to your controller, where we can effect either control to increase or to reduce the flow rate on our pipeline system. So this is the orifice split that we were talking about the other time. So you see one of the end is beveled, and this end that is beveled is always facing the downstream, okay, of your flow. Okay, so these are impulse lines to your differential pressure meters. Okay, so this is the orifice plate and this is the differential pressure meter or indicator stroke a transmitter. Okay, like we saw earlier, that will help to transmit the signal to your control room, to your controller, to effect whatever change that you want on your final control element, which is the valve, or to your control room to indicate the flow rate on this particular pipeline. So we also have other types of differential pressure flow meters. We have the pitot tube. Okay, we have the pitot tube and we also have the venturi tube. Okay, so what they also do is to find a way of creating pressure difference along the stream and measure that pressure difference. So like in the previous case with the orifice plate, the pressure difference increases with increase in flow. So let's take the example of the pitot tube now. So you see that here helps us to measure the static pressure, which is like this end of the differential pressure meter. Okay, so here helps us to measure the static pressure, which is here. Then here we'll be looking at the dynamic pressure. So which means that as the flow rate is increasing, you'll see that the pressure on this tube, okay, in this tube I mean to say, will also be increasing. And you see that will increase this leg of the manometer. So the differential pressure, you see it will be going up as the pressure is increasing. So these two legs, okay, could be connected to a differential pressure transmitter, and that will help us to look at the pressure on the line. So like in the case of the the case of the orifice plate, orifice meter, you see that as the flow velocity is increasing, which is the flow rate, you will see that the differential pressure will also be increasing. Okay, so the static pressure will remain constant, and as the flow is increasing, since this the flow velocity does not have much effect on the static pressure, you see that the dynamic pressure will be getting up. Okay, so it will rise to a stage that will now come to the stagnation pressure. Okay, and the pressure will just be steady at that end. So that is the dynamic pressure. Is the stagnation pressure is the sum of this static pressure and this dynamic pressure. Okay, but the difference basically is determined by the flow rate in the pipeline. So this is an example of a venturi tube. Okay, so you see the tapered end. This is the tapered end. So it's just like this end now. Remember, our goal is to create a restriction on the flow. Okay, as you do that, then the flow velocity will momentarily reduce. That will make pressure want to go up, which is indicated on this leg of the impulse line. And then as the flow is throttled, the velocity will increase, and that will reduce the pressure. So this pressure differential, okay, caused by the venturi action, is actually determined by the flow rates across this section of the pipeline. So that is what we have here. You see the two impulse line taken to your flow meter wherever it is, and this is it. Okay, so here from the high pressure end, okay, and then this from the low pressure end to your pressure transmitter that is wired to your controller or your control room, and to your control to your control room or controller, and then to the final control element, which is the control valve. So this is how it is installed in the field. This is the pitot tube type of a flow meter. Okay, so like the pitot tube, it does not create that restriction, so there is no pressure difference as we saw here. But there is a drawback. If the fluid is contaminated, that can, by debris, that can cause plugging of this high pressure end, okay, of your pitot tube meter. Okay.